The Pantheon has stood for almost 2,000 years without a crack. Modern concrete often fails in mere decades. This stark contrast hides a lost secret with the power to reshape our world. By the end of this exploration, you will understand the exact chemical recipe that made ancient Roman concrete virtually indestructible, and how recovering it could launch a green building revolution. We will uncover why a material that thrives in seawater was forgotten for centuries, and what rare mineral holds the key to its self-healing power. What does it truly mean to build something that lasts forever? Beneath the turquoise waters of the Mediterranean, off the coast of Caesarea, lies a testament to forgotten genius. Massive concrete blocks, part of an ancient Roman harbor breakwater, have endured the relentless force of the sea for over 2,000 years. While modern ports require constant repair, these submerged ruins have not just survived, they have grown stronger. They are the timeless witnesses, challenging everything we assume about durability and progress. This is not a story of myth, but of physical, empirical evidence waiting on the seafloor. Marine archaeologists and materials scientists treat these sites as a unique natural laboratory, one that has been running a continuous experiment for centuries. The key finding is as astonishing as it is counterintuitive. Modern Portland cement concrete, when exposed to salt water, typically corrodes. Chlorides attack the steel reinforcement, causing it to rust and expand, which cracks the concrete from the inside out. But Roman maritime concrete performs the opposite magic. It actually thrives in salt water, becoming more resilient over time. Sites like Portus Cosanus in Italy tell the same story. Their volcanic rock and mortar mixtures fused into a single, indestructible mass by the sea itself. Even on land, structures like the cylindrical tomb of Caecilia Metella on the Appian Way showcase a different facet of this durability, its concrete shell resisting centuries of weathering and conflict. Picture the stark contrast, a modern seawall crumbling after 50 years of service, sitting just miles from an ancient Roman counterpart that has withstood 2 millennia of storms. It forces a profound question. What if our definition of technological advancement is flawed? What if progress isn't always about inventing something new, but sometimes about rediscovering something profoundly old and wise? This physical evidence, written in stone and seawater, points unequivocally to a radical difference in the recipe. The Romans were not just building structures, they were cultivating a chemical partnership with time itself. The Romans began with a simple powder, a gift from the earth itself. Quarried from the slopes of volcanoes like Vesuvius, a fine, sandy ash known as Pozzolana was the first and most critical ingredient in their formula. This was not ordinary dirt, it was a siliceous and aluminous material, rich in silica and alumina, that possessed a hidden reactive power. When mixed with lime and water, it did not simply harden, it underwent a profound chemical transformation. Geologists note that the unique mineralogy of this volcanic ash, including crystals like leucite and philipsite, is what made it so special. These minerals are highly reactive, eager to form new bonds. This leads us to the heart of the process, the pozzolanic reaction. In simple terms, when lime, which is calcium oxide, is mixed with water, it becomes calcium hydroxide, a relatively weak substance. But when pozzolana ash is introduced, its silica and alumina react with that calcium hydroxide. They do not just mix, they chemically fuse to create an incredibly stable network of calcium silicate hydrate compounds. This is the binder that holds Roman concrete together, a matrix far more durable and resilient than anything produced by lime alone. The Romans were meticulous about their sources. The very best pozzolana came from specific regions, most famously the area around Pozzuoli in the Bay of Naples. they understood that the granularity and mineral composition of the ash from different volcanoes affected the final product's strength and setting time. Think of pozzolana not as a filler but as a catalytic agent. In a modern chemical process, a catalyst is not consumed. It enables a reaction to happen that otherwise would not, or would happen far too slowly. Pozzolana acted in a similar way, enabling a slow, steady, and supremely strong chemical bond to form over time, a process that could continue for centuries. So here we have a powerful, readily available material, understood and perfected by an ancient civilization. This raises a compelling question. If this volcanic ash was so effective and its sources so well known, why did this knowledge vanish for so long? The answer lies not just in the first ingredient, but in the second, a component so unusual it seems almost like alchemy. That volcanic ash needed a partner to unlock its potential, a substance so reactive it was considered dangerous in its raw form. This was quicklime, the pure, caustic heart of Roman concrete. To produce it, Roman builders would load chunks of limestone into a simple but effective kiln, a stone or brick furnace. They would then burn wood or charcoal in a fire reaching temperatures over 900 degrees Celsius. This intense heat drove off carbon dioxide from the limestone in a process called calcination, leaving behind a brittle, white substance, calcium oxide. This was quicklime, a material so chemically hungry it would hiss and steam violently if exposed to moisture in the air. The next step was where Roman craftsmanship turned chemistry into an art. They would take this dangerous powder and carefully slake it, mixing it with water. This wasn't a gentle process, it was an exothermic reaction, releasing tremendous heat. The quicklime would seem to boil as it combined with the water, transforming into calcium hydroxide, a creamy paste known as lime putty. Historical chemists studying ancient texts and mortar samples propose a fascinating theory. The Romans likely didn't let this paste sit and mellow for long periods as some traditional masons did later. Instead, they may have used a hot mixing technique. Imagine them combining the freshly slaked, still warm lime putty directly with the volcanic pozzolana and coarse aggregates like fist-sized chunks of rock or brick. This mixture, still chemically active and hot, would be poured into wooden molds to set. The internal heat from this reaction is now believed to be crucial. It may have initiated beneficial chemical processes from the very beginning, creating a more chaotic, less ordered microscopic structure within the concrete. This sounds like a flaw, but in materials science, this specific kind of disorder can be a strength. It creates a landscape full of tiny weaknesses and reactive sites. Later, when water eventually seeped into these microscopic cracks over centuries, it could react with the unused quicklime particles trapped inside, forming new crystals that would literally glue the fissures shut. This is the proposed mechanism for the legendary self-healing property. The evidence for this hands-on process is etched into the landscape. Archaeologists find the remains of lime kilns very close to major Roman construction sites, like the bustling port of Portus near Rome. The fuel needed to produce quicklime was immense, so it made sense to produce it locally. Analysis of concrete samples from structures like the markets of Trajan reveal a consistent ratio, roughly 1 part lime to 2 parts pozzolana ash, a formula refined through generations of trial and observation. This was not abstract science, it was embodied empirical knowledge. A Roman builder understood his materials through sight, touch, and experience, knowing exactly how the mix should feel and react. We can compare it to a traditional baker working with a sourdough starter, sensing the right consistency and activity through practice, not a printed recipe. This deep, tactile understanding of materials is what faded after the empire's decline. The knowledge of how to handle this reactive, almost living paste was gradually replaced by simpler, more predictable, but ultimately less resilient methods. So we have the reactive volcanic ash and the carefully prepared lime binder. But to trigger the final, enduring transformation, they required one more elemental catalyst. This brings us to the surprising and often misunderstood role of the third ingredient, not as a passive component, but as an active chemical participant in the concrete's long life. For Roman engineers, the sea was not an enemy to be resisted, but a powerful ally to be harnessed. In a stroke of brilliant chemical intuition, they did not use precious fresh water to mix the concrete for their harbors. They used seawater itself, drawn directly from the very element that would test their structures for eternity. This was the final, paradoxical ingredient. Where we see a corrosive force, they saw a liquid catalyst. Modern concrete, when exposed to seawater, suffers from what engineers call sulfate attack. Sulfate ions from the salt penetrate the material and react with certain compounds, forming expansive crystals that generate internal pressure, spalling, and cracks. It is a slow, destructive process. Roman concrete experienced something entirely different, a constructive chemical cascade. When seawater met the hot mixture of lime and volcanic ash, it initiated a slow, centuries-long conversation. Researcher Marie Jackson and her team, using advanced tools like X-ray microdiffraction, discovered something remarkable within 2,000-year-old samples from the harbor at Tuscania. They found the growth of rare, plate-like minerals, primarily a calcium-aluminum silicate hydrate called Aluminous Tobermorite. This mineral does not typically form at the low temperatures found in seawater environments. Its presence is a fingerprint of a unique, long-term reaction. Here is the elegant alchemy: the magnesium and sulfate ions in seawater, the very agents of destruction for modern materials, reacted with the leftover lime and the alumina from the volcanic ash. Over decades and centuries, this reaction produced not destructive crystals, but these interlocking plates of tobermorite and a related zeolite mineral called philipsite. Think of the concrete not as a static, inert block, but as a dynamic, porous landscape. As tiny cracks naturally begin to form from stress or movement, infiltrating seawater finds a reservoir of reactive material, the unused lime and ash. It then deposits these new, strong mineral crystals precisely in those fissures, gluing them back together. The material does not just resist degradation, it actively repairs itself, and in doing so, can actually become denser and stronger over time. This is the ultimate contrast. Modern concrete in the sea fights a losing battle, its chemistry working against it until it fails. Roman concrete entered into a symbiotic relationship with its environment, using the sea's own chemistry to continually fortify itself. It became less like a manufactured product and more like a living rock, a coral reef of human ingenuity that grew more resilient with age. This forces us to reconsider our definitions of waste and resource. The Romans viewed the corrosive salts of the ocean as a valuable component, a building block. Their methodology was one of integration, not insulation. To unlock this full potential, however, required one final, masterful technique in how they combined these elements, a process so specific its loss would render the recipe inert for 1,000 years. The air at a Roman construction site would have been thick with the scent of wet stone and the sharp, acrid smell of chemistry in action. Laborers, their muscles straining, worked not with passive bags of powder, but with a living, reactive material. They would pour quicklime into troughs, adding water to initiate a furious, steaming reaction. But instead of letting this lime putty cool and settle, they acted with urgent purpose. While the mixture was still hot and violently reactive, they would vigorously incorporate the volcanic pozzolana ash and coarse aggregates, chunks of tough rock, or even broken bricks and pottery. This was the lost methodology, hot mixing. The Roman architect Vitruvius, in his 10 books on architecture, gave precise instructions for mortar preparation, emphasizing the purity of the lime and the quality of the ash. but the true craft was in the energetic, almost violent incorporation. Using heavy wooden paddles, teams would work the steaming mass, ensuring every piece of rubble was coated in the reactive lime pozzolana paste. This was not a gentle stir, it was a deliberate, energetic kneading. The heat generated was not a byproduct to be avoided, it was a crucial part of the recipe. Experimental archaeologists recreating the process have found that this internal heat, often reaching temperatures that would be uncomfortable to touch, did something remarkable. It created a more homogeneous and cohesive paste from the very beginning, encouraging the initial formation of those beneficial calcium-aluminum silicate hydrate bonds. Think of it like making a perfect sourdough bread. The initial mixing and kneading of a warm, active starter into the flour is not just about combining ingredients. It is about developing the gluten network that will give the bread its structure and strength. The temperature and vigor of that process determine the final texture of the loaf. In Roman concrete, the heat and energetic mixing developed the initial chemical network, creating a less ordered, more chaotic microstructure at the microscopic level. This chaotic landscape, full of tiny reactive sites and pockets of unused lime, is precisely what gave the concrete its legendary long-term potential. It was designed from the outset to be imperfect in a specific, brilliant way, leaving room for future chemical reactions to fill the gaps. This practical, observable technique was a triumph of embodied knowledge, a craft passed from master to apprentice on bustling sites across the empire. Its abandonment after Rome's decline is a profound mystery of technological history. Why would such a visibly effective method, one that produced structures lasting generations, simply fade away? The answer involves complex shifts in society, economy, and knowledge transmission. But it also leads us to the final masterstroke of the Roman formula, the sophisticated and often surprising materials they chose to bind together within this reactive matrix. Within that reactive, steaming paste, Roman builders embedded a carefully chosen skeleton of stone. This was the key mentor, the coarse aggregate that gave the concrete its bulk and its remarkable resistance to cracking. Far from being simple filler, the selection of these chunks of rock, brick, and ceramic was a deliberate science. Roman engineers understood that the strength of the whole depended on the character of its parts. They sought out materials with specific physical properties, favoring volcanic rocks like tuff, which is lightweight yet strong, and travertine, known for its load-bearing capacity. The iconic Colosseum, for instance, uses a travertine aggregate in its lower levels, providing immense compressive strength to support the towering weight of the structure above. But it wasn't just about the type of rock, it was about its shape and texture. Structural engineers note that the angular, rough surfaces of freshly quarried or broken volcanic rock created a far superior mechanical bond with the lime pozzolana mortar. Think of it like Velcro, the jagged edges and porous surfaces of the aggregate locked into the paste, creating a unified mass that resisted shearing and pulling forces. Smooth, rounded river gravel, by contrast, would simply slide within the matrix, a weakness the Romans intuitively avoided. They also mastered the art of particle size distribution, though they would not have called it that. By intuitively mixing a careful gradation of large, fist-sized pieces with medium and small fragments, they minimized the empty spaces or voids within the concrete. This created a denser, more homogeneous material. Imagine building a stone wall. If you use only large, irregular boulders, there will be huge gaps between them. If you use only small, uniform pebbles, they can shift easily. But if you skillfully combine boulders, stones, and gravel, the smaller pieces fill the spaces between the larger ones, locking everything into a tight, interlocking puzzle. This is precisely what the Romans achieved within their concrete mixes. The aggregate formed a rigid, internal architecture that distributed stress efficiently throughout the entire structure. Perhaps most ingenious was their strategic use of different aggregates for different purposes. The Pantheon's majestic dome, the largest unreinforced concrete dome in the world, stands as the ultimate example. To reduce the crushing weight at its top, builders used progressively lighter aggregates as the dome rose. At its base, heavy travertine and tuff provided stability. But in the upper layers, they incorporated porous, frothy volcanic pumice and even empty clay amphorae. This wasn't just random recycling. It was a calculated engineering decision to lighten the load without sacrificing structural integrity. Furthermore, the Romans were masters of reuse, incorporating broken bricks, tiles, and pottery, materials archaeologists call spolia, into their mixes. This practice gave a second life to materials and often improved the concrete's properties, as these ceramic fragments were highly porous and created an excellent bond with the mortar. It prompts a reflective question for our own era, obsessed with newness and disposal. What could we learn from this ancient model of circular economy, where waste was not an endpoint, but a valuable component in building something meant to last forever? This carefully graded skeleton, locked within its self-healing binder, created a composite material of extraordinary resilience. Yet for all its physical genius, the true longevity of Roman concrete may owe as much to a philosophical principle as to chemistry, a worldview that saw construction not as a finite act, but as the beginning of a dialogue with time itself. At the microscopic level, the secret of Roman concrete reveals itself as a breathtaking landscape. When scientists place a tiny sample under an electron microscope, they do not see a uniform, inert slab. Instead, they discover a complex, interlocking tapestry of crystals, a miniature fortress of stone. This is not a flaw, but the engineered source of its immortal strength. The two most important minerals in this tapestry are aluminous tobermorite and philipsite. Aluminous tobermorite forms as thin, plate-like crystals that grow within the lime-rich regions and the tiny pores of the concrete. Think of these plates as microscopic shingles or scales, overlapping and interlocking to create an incredibly tough, layered armor within the material. Philipsite, a zeolite mineral, often grows in needle-like clusters, weaving through the matrix and further reinforcing it. These crystals are exceptionally rare in modern concrete, and when they do appear, they are often unstable and short-lived. In Roman concrete, they are the stable, enduring foundation. The process of their formation is a masterpiece of slow chemistry. It begins with the pozzolanic reaction we discussed, but it does not end when the concrete sets. Over decades and centuries, as minuscule amounts of water seep through the material, they continue to react with the reservoirs of unused lime and reactive volcanic glass. This ongoing, glacial pace reaction allows the tobermorite and philipsite crystals to nucleate, grow, and mature, slowly but surely densifying the concrete from the inside out. They act like a permanent, internal reinforcement system, blocking the path of potential cracks by forcing them to navigate a tortuous, crystalline maze. This stands in stark contrast to the inner world of modern Portland cement concrete. Its binding phase is primarily a faster-forming, more amorphous calcium silicate hydrate gel. While strong initially, this gel is more prone to chemical attacks and can shrink as it cures, creating internal stresses and micro-cracks from the very beginning. It is designed for rapid strength gain, not for centuries of graceful aging. A useful analogy is to think of modern concrete as a hardened block of plaster. It is solid but relatively homogeneous and brittle. Roman concrete, with its intricate crystalline tapestry, is more like a naturally occurring composite material, such as fiberglass or bone. In fiberglass, the strength comes from the glass fibers embedded in the plastic resin, the two materials working together to create something tougher than either alone. In Roman concrete, the crystalline plates of tobermorite are the reinforcing fibers, and the surrounding cementitious paste is the matrix. This design gives it both compressive strength and a remarkable resistance to tensile stress, the kind of pulling force that causes cracks. This invites a profound shift in perspective. For over a century, our material science paradigm has prioritized speed and immediate, measurable strength. We design materials to reach their peak performance in 28 days. The Romans, whether by brilliant intuition or accumulated experience, designed a material for long-term evolution. They engineered not for a finished state, but for a beneficial chemical journey that would span generations. What if the ultimate measure of a material's intelligence is not how strong it is today, but how wisely it uses time to grow stronger tomorrow? This leads us directly to the most magical property of all, the concrete's ability to not just resist damage, but to actively repair itself, a process written in the language of water and chemistry. A microscopic crack begins its journey through the dense matrix of ancient concrete. Instead of widening into a fatal flaw, it encounters something unexpected, a reservoir of potential. Deep within the material, pockets of unreacted lime and fragments of volcanic glass, dormant for centuries, are suddenly exposed by this tiny fissure. When mineral-rich water seeps into this newly opened space, it does not bring destruction, it initiates repair. The water dissolves calcium ions from the lime, and these ions immediately seek out the reactive silica and alumina from the exposed pozzolana. They combine, restarting the ancient pozzolanic reaction right at the site of the damage. Slowly, imperceptibly, new plate-like crystals of aluminous Tobermorite and philipsite begin to precipitate. They grow across the gap, layer upon layer, until the crack is completely filled and sealed with a material as strong as the original concrete. This is not a metaphor. It is a documented chemical process, a form of autonomous healing written into the very recipe. Recent laboratory experiments have brought this phenomenon into stunning clarity. Scientists like those at the University of Utah have created precise replicas of Roman maritime concrete, following the hot mixing methods described by Vitruvius. They then deliberately induced controlled cracks in these samples and immersed them in tanks of simulated seawater. Using advanced imaging techniques over months, they watched as the cracks, once clearly visible under a microscope, gradually became fainter and then vanished altogether. The new mineral growth was not a superficial patch, it was a full-depth structural repair. This process offers a powerful analogy to a natural system we all understand, the human body's response to a cut. When skin is broken, platelets in the blood rush to the site, clumping together to form a temporary plug. Then, a more complex cascade of cellular activity begins, producing collagen and other proteins to rebuild the tissue, often leaving a scar that is stronger than the surrounding area. Roman concrete operates on a similar principle of triggered regeneration. The crack is the injury, the infiltrating water is the carrier, and the reservoirs of reactive lime and ash are the platelets and building materials, mobilizing to seal the breach permanently. This capacity for self-repair fundamentally changes our relationship with the built environment. Modern infrastructure is designed with the assumption of eventual decay, leading to a costly and endless cycle of inspection, maintenance, and replacement. We fight a defensive war against time and the elements. Roman engineering, whether by profound insight or brilliant accident, proposed a different strategy, a partnership. It designed a material that could engage with its environment in a constructive dialogue, using the very agents of decay, like seawater, as the catalyst for its own renewal. This invites a transformative question. What if our bridges, seawalls, and buildings were not static objects slowly eroding, but dynamic systems with a built-in capacity to heal? The emerging field of bio-inspired materials is already exploring this very idea, developing modern concretes with embedded bacteria or microcapsules that release healing agents when cracked. Yet the Roman model achieves this without any added biological components or complex microtechnology, using nothing more than a specific chemistry of earth, fire, and water. Contemplating this leads to a deeper historical wonder. If this knowledge produced harbors that lasted 1,000 years and domes that still stand, why did such a transformative technology fade into obscurity for so long? The answer lies not in a single event, but in a slow unraveling of the complex system that created and sustained it. The highly organized, resource-rich Roman economy that quarried specific volcanic ash from Pozzolana and transported it across the empire collapsed. The guilds of master builders and the chain of apprenticeship that passed down the tactile, hands-on knowledge of hot mixing and material selection fragmented. In the post-Roman world, priorities shifted dramatically towards speed, simplicity, and immediate necessity. Building a defensive wall quickly from locally available rubble and simpler lime mortar was more urgent than crafting a pier meant to endure for the ages. The profound, long-term wisdom encoded in the Roman recipe became a victim of shorter time horizons. The knowledge did not disappear in a day. It eroded over generations until the method became a legend, and the surviving structures were regarded not as examples of replicable science, but as magical relics of a lost golden age. Their concrete was seen as a mystery rather than a method waiting to be rediscovered. The bustling quarries of Pozzolana fell silent. Across the empire, the intricate supply chains that delivered specific volcanic ash from Italy to construction sites from Britain to Syria began to fray and then snap. This was not a sudden, dramatic erasure of a secret formula, but a slow fading like a fresco exposed to centuries of damp air. The disappearance of Roman concrete was a symptom of a much larger transformation, the unraveling of a vast, interconnected system that had sustained its creation. As the Western Roman Empire's political and economic unity fragmented in the 4th and 5th centuries, the specialized knowledge housed within its guilds began to evaporate. These guilds, the Collegia Fabrum, were far more than labor unions. They were living repositories of engineering wisdom. Within them, masters taught apprentices not from textbooks, but through hands-on practice, the exact feel of the hot lime mix, the visual cue for the right ash consistency, the auditory knowledge of how the aggregate should sound when mixed. This was tacit knowledge carried in the muscles and memories of craftsmen, and it was incredibly vulnerable. When long-distance trade collapsed, builders could no longer access the premium pozzolana from specific volcanic regions. When large-scale public works projects funded by a centralized state dwindled, the demand for such a high-performance, long-term material vanished. The priority shifted decisively from monumentality and permanence to immediacy and defense. Kings and local lords needed fortified walls and simple churches built quickly from readily available local stone and rubble, bound with simpler, faster-setting mortars. The sophisticated, slow-curing concrete of the Caesars had no place in this new, fractured world. Historians note this shift in architectural priorities is vividly etched in the landscape. Compare the soaring, confident vault of the Pantheon, a public testament to civic grandeur, with the thick, defensive walls of a typical early medieval fortress. The former was an investment in a timeless future, the latter a pragmatic response to an uncertain present. Byzantine architecture, while magnificent in its own right, moved decisively away from concrete vaulting, favoring brick and stone, materials that were easier for local workshops to produce and assemble without the deep chemical understanding of the old Roman methods. The recipe was never truly lost in the sense of being destroyed. It was simply no longer taught, no longer practiced, and therefore no longer remembered. It became a ghost in the historical record, its principles lingering only in the silent, enduring stones that later generations would look upon with a mixture of awe and superstition, attributing their survival to lost magic or superior ancient virtue rather than recoverable science. This pattern echoes throughout history, from the precise anti-seismic masonry of the Incas to the legendary strength of Damascus steel. Advanced technologies are not just collections of facts, they are ecosystems of knowledge requiring stable societies, economic networks, and chains of mentorship to survive. When those conditions disappear, the technology often fades with them, leaving behind only tantalizing artifacts of its power. This realization frames the modern quest not as mere curiosity, but as a form of archaeological rescue, a race to decode the silent language of stones before the last echoes of their making fade completely. For over a millennium, the formula was a ghost, its presence felt only in the silent endurance of the ruins it left behind. Unlocking it would require a new kind of inquiry, one that treated history as a crime scene and science as the detective. This is the modern investigation into Roman concrete, a collaborative manhunt across disciplines where geologists, chemists, and archaeologists work in unison, piecing together clues that have been cold for 1,500 years. The case file is not paper but stone, and the witnesses are mineral crystals that formed during the reign of Augustus. Leading this forensic effort are researchers from institutions like the University of Utah and Lawrence Berkeley National Laboratory. They approach each ancient structure not as a monument but as a unique data vault. Their primary challenge is a profound one. How do you study a 2,000-year-old material without destroying the irreplaceable artifact that contains it? The answer lies in a suite of non-destructive tools that act like high-tech eyes, seeing deep into the molecular heart of the concrete. A scanning electron microscope, for instance, does not just magnify the surface, it allows scientists to map the intricate topography of a sample at a scale smaller than a grain of pollen. They can see the plate like crystals of Tobermorite interlacing like miniature armor. Even more revealing is X-ray microdiffraction, a technique that shoots a beam of X-rays at a tiny spot and analyzes how the rays scatter. This tells researchers not just what minerals are present, but their precise crystalline structure and orientation, revealing the history of the chemical reactions that formed them. Spectroscopy adds another layer, identifying the elemental fingerprints of the volcanic ash and lime. Think of these tools as a detective's kit for the atomic world. The electron microscope is the magnifying glass that finds the trace evidence. The X-ray diffractometer is the lab analysis that identifies the unique composition of a fingerprint. And spectroscopy is the database check confirming the origin of the materials. But before any of this analysis can begin, the team faces its first major hurdle, obtaining a pure sample. A structure like the markets of Trajan in Rome has stood through earthquakes, fires, and centuries of repair. Drilling a core sample from such a protected monument is a delicate operation of both engineering and diplomacy. Researchers must pinpoint a location likely to contain original, undisturbed concrete, avoiding areas patched in later centuries. The drill itself is a specialized, low-vibration coring tool designed to extract a slender cylinder of material, often no wider than a coin, with minimal impact to the structure. The extracted core becomes a priceless timeline, a physical record of the concrete's entire history, from its initial pour to its present state. The timeline of major discoveries in this case reads like a series of thrilling breakthroughs. In the 1990s, advanced microscopy first definitively identified the presence of the rare mineral Tobermorite within Roman maritime concrete, providing the first hard evidence of its unique chemistry. This was the initial clue that the Roman material was fundamentally different. Years later, the use of synchrotron-based X-ray techniques allowed teams to map the distribution of elements within the concrete, revealing the slow migration of minerals over centuries. But perhaps the most pivotal breakthrough came more recently, when experiments replicating the Roman hot mixing method finally demonstrated the intentional creation of those reactive lime clasts, the key to the self-healing mechanism. Each finding is a piece of the puzzle snapping into place. What must it feel like for those scientists to be the first people in over 1,000 years to not just admire these structures, but to truly understand the brilliant logic of their making? To shift from wondering how they survived to knowing exactly why they did. This forensic journey does more than satisfy historical curiosity. It provides a precise blueprint, a chemical recipe that had been missing from the human library for generations. And with that blueprint now in hand, the most urgent question becomes a practical one. Can we actually use it? The recipe was never truly lost. It was simply waiting, encoded in a 2,000-year-old text. For modern investigators, the most tantalizing clues lie not in the ruins themselves, but in the words of a Roman architect named Vitruvius. His 10-volume work on architecture is the only major surviving technical manual from the ancient world. Within its pages, in Book 2, he provides the closest thing we have to an official recipe. He describes a pit sand found around the Bay of Naples and near several Italian cities that, when mixed with lime, produces a mortar of exceptional strength, even for structures in the sea. This pit sand is, of course, Pozzolana. But for all its historical value, Vitruvius' text is a labyrinth of cryptic advice and frustrating omissions for a modern scientist. He gives no precise ratios, no chemical formulas, and his terminology for materials is often vague by today's standards. Translating his Latin presents the first major hurdle. The word he uses for lime, calx, is clear, but his descriptions of the different types of stone to burn for that lime, or the specific qualities of the best volcanic ash, rely on observational terms that are open to interpretation. Was the white, brittle stone he recommends for the highest quality lime a specific type of pure limestone, or a more general category? Classicists and engineers must work in tandem, cross-referencing his words with archaeological finds from known Roman lime kilns to build a practical understanding. Vitruvius is more detailed on procedure than on precise measurements. He emphasizes the importance of slaking the lime thoroughly and mixing it with the ash for a very long time. One famous passage advises that the longer the mixture is worked, the better and stronger it will be. This aligns perfectly with the modern understanding of the hot mixing method, where prolonged, energetic kneading develops that crucial initial chemical network. He also stresses using the freshest lime possible, a clue that the Romans understood the material's reactivity diminished if left exposed to air. To fill in the gaps, scholars turn to other fragmented references. Pliny the Elder, in his Natural History, briefly mentions a dust that, when combined with lime and rubble, hardens into a mass that even the waves cannot break. Frontinus, the water commissioner of Rome, notes the use of a specific mortar in aqueducts that set underwater. None of these sources, however, provide a complete step-by-step manual. They offer glimpses like pieces of a shattered mosaic. Imagine a modern builder, armed only with an English translation of Vitruvius, trying to recreate the concrete. They would know they need volcanic ash and lime. They would know to mix it vigorously, but critical questions would remain unanswered. Exactly how much water to add? What is the ideal temperature of the mix when it is poured? How long should it cure before being submerged? The text assumes a world of shared, practical knowledge that its original readers possessed, knowledge that has since evaporated. This reveals the profound gap between explicit, written knowledge and the tacit, hands-on skill of the Roman craftsman. The written word could record the ingredients and the broad strokes of the method, but it could not capture the muscle memory, the intuitive sense of consistency, or the experiential wisdom of when the mix was just right. This gap is why the text alone was not enough to revive the technology after the empire's fall. You could read Vitruvius for centuries and still not know how to make the concrete, because the true mastery was in the doing, not the describing. This very challenge, however, points the way forward. If the ancient texts provide the ingredients list and basic instructions, then the only way to recover the lost meal is to get into the kitchen and start cooking. This necessity births the next thrilling phase of the quest, the experimental archaeology that turns vague descriptions into tangible, testable stone. The air inside the modern laboratory is cool and sterile, a world away from the dusty heat of a Roman construction site. Here, researchers clad in white coats and safety goggles measure powdered ingredients with digital precision, attempting to resurrect a recipe through the lens of 21st century science. This is experimental archaeology at its most direct, where hypotheses about the past are tested not with shovels, but with chemical formulas and scanning electron microscopes. The goal is deceptively simple: to mix a batch of concrete in the present that will behave exactly like the concrete from 2,000 years ago. The process begins with sourcing the raw materials. Teams procure volcanic ash not from Pozzolana, but from geologically similar deposits in the American West or elsewhere, analyzing its mineral content to ensure a close match. They burn pure limestone in a kiln to create quicklime, carefully slake it, and then comes the critical variable, the mixing itself. Some experiments follow the hot mixing hypothesis, combining the materials while the lime putty is still warm and reactive, manually working the thick, gravelly paste to replicate that ancient energetic kneading. Other batches are mixed cold as a control to isolate the effects of temperature. Every variable is a question: the type of aggregate, the ratio of ash to lime, the salinity of the mixing water, even the humidity of the curing room. Chemists monitor the batches with an array of sensors, tracking the internal temperature over days as the chemical reactions proceed. They test the workability, how easily the concrete can be placed and shaped, and its initial set time. But the true test of success is not measured in hours or days, it is measured in months and years. Samples from each experimental batch are cast into small cylinders or cubes, and then placed into different environments, some in freshwater tanks, others in circulating seawater simulants, and some left in controlled atmospheric chambers. This is where patience becomes the most vital instrument in the lab. Researchers must wait, allowing time to do its work, before they can destructively test these samples to see what has formed inside. The process is deeply iterative, a cycle of mix, cure, analyze, and adjust. A batch mixed one year might be analyzed the next, its compressive strength measured by a hydraulic press, and its internal structure scrutinized under a microscope. The moment of validation is profound. When a sample that was mixed hot and cured in simulated seawater is cracked open and placed under the electron microscope, the sight of those distinctive, interlocking plates of aluminous Tobermorite is a silent triumph. It is the fingerprint of success, proving the modern recipe has initiated the same slow, strengthening conversation with its environment. In one landmark experiment, scientists deliberately cracked a recreated sample, immersed it in a brine solution, and then used microcomputed tomography, a kind of three-dimensional X-ray, to observe it over time. Week by week, they watched as the crack first stabilized, then began to fill with new, white mineral deposits, until it was no longer visible to the scanner. They had not just recreated the material, they had witnessed its legendary self-healing in action. This journey from mixing trough to validated sample is a powerful bridge across centuries. It transforms the ruins from mystical relics into reproducible engineering. Yet this successful resurrection prompts a new set of practical and ethical considerations. Now that we hold the recipe in our hands, what do we do with it? Is it ethical to use a material whose production requires burning limestone, a process that releases carbon dioxide, even if the final product lasts for millennia? This question of environmental cost versus longevity becomes the critical lens through which we must view this rediscovered knowledge, forcing a direct comparison with the material that defines our modern world. The modern world is built on a foundation of Portland cement, a material whose creation exacts a heavy toll on our atmosphere. To produce it, limestone and clay are baked together in colossal rotating kilns at staggering temperatures, often exceeding 1,400 degrees Celsius. This process, known as clinkering, not only consumes vast amounts of fossil fuel energy, but also chemically releases carbon dioxide from the limestone itself. For every ton of cement produced, nearly a ton of carbon dioxide is emitted into the air. Now hold that image in your mind and contrast it with the Roman method. Their lime was produced in simpler, smaller kilns at several hundred degrees lower, a significant energy saving. More importantly, their concrete strength did not come from this lime alone, but from the abundant, naturally reactive volcanic ash that comprised the bulk of their binder. They were leveraging a geologically pre-processed material, requiring no additional extreme heat. This stark difference frames the Roman recipe not as a relic, but as a remarkably prescient model for low-carbon construction. Environmental engineers point to a powerful metric. The global cement industry is responsible for approximately 8% of all human-made carbon dioxide emissions annually. If we could replace even a portion of that Portland cement with supplementary cementitious materials like the Roman pozzolans, the impact would be transformative. This is where ancient insight meets modern innovation. Today's most promising sustainable cements, often called geopolymers or alkali-activated materials, are essentially the high-tech descendants of that Roman principle. Instead of using purely volcanic ash, they frequently employ industrial byproducts like fly ash from coal plants or ground granulated blast furnace slag from steel production. These materials are rich in silica and alumina, just like pozzolana. When activated with an alkaline solution, they undergo a similar geopolymerization reaction, forming a strong, durable binder without the need for Portland cement clinker. This creates a powerful circular economy, turning waste streams from other industries into valuable construction materials, locking potential pollutants into a stable, long-lasting stone. Consider a practical scenario: the construction of a new coastal seawall. A conventional design using modern reinforced concrete would have a massive upfront carbon footprint from cement production. A design utilizing a high volume of fly ash or natural pozzolan, inspired by the Roman maritime formula, could cut that embodied carbon by 40% or more. Furthermore, if that concrete is engineered to self-heal, its lifetime maintenance carbon cost plummets, as it requires fewer repairs and less frequent replacement over a century of service. The math becomes compelling: a greener material that also promises to endure. So this leads to a pressing question: if this path is so clearly beneficial, both environmentally and potentially economically in the long run, why isn't every new building project using Roman-inspired concrete? The answers lie in the very systems that shape our modern world. Our entire construction industry, from building codes and material standards to contractor training and liability insurance, is built around the predictable, fast-curing properties of Portland cement. A new material, even a 2,000-year-old one, represents a risk. Supply chains for consistent, high-quality natural pozzolans or industrial byproducts are not yet as robust as those for cement. The slower curing times of some geopolymer mixes can clash with the fast-paced schedules of modern development, where time is literal money. There is also a knowledge gap. The deep, tactile understanding Roman masons had of their materials has been replaced by standardized testing protocols, and new materials require new protocols to be written and accepted. The challenge, therefore, is not merely chemical but systemic. It requires rebuilding not just our concrete but the very framework of how we build. The laboratory success of Roman-inspired concrete presents a beautiful blueprint, but the path from the controlled environment to the construction site is paved with practical hurdles. One of the most immediate technical barriers is time itself. Roman concrete was designed to gain strength over decades, not days. Its slower initial set and cure times clash directly with the breakneck pace of modern commercial construction, where delays translate directly into immense financial penalties. A developer cannot wait months for a foundation to fully cure before framing the next floor. This fundamental mismatch in timelines is a primary reason why the fast-hardening Portland cement paradigm dominates. Furthermore, the original recipe relies on specific volcanic materials. Not every region has a ready supply of high-quality pozzolana ash, and transporting it over long distances negates the environmental benefits and increases costs. This creates a supply chain problem, making the material less universally viable than the globally standardized bag of Portland cement. Perhaps the most significant obstacle for engineers, however, is the lack of long-term performance data. Modern building codes, which are written in the language of liability and safety, demand extensive, quantifiable proof of a material's behavior over decades under specific loads and conditions. We have 2,000-year-old Roman harbors as evidence, but for a city planner approving a new bridge or skyscraper, that historical data, while compelling, does not substitute for the certified, standardized test results that exist for conventional reinforced concrete. The risk is simply too great to build a $100 million project on an ancient principle without modern validation. Industry professionals explain that this is not just a technical issue, but an economic and cultural one. The entire global construction ecosystem, from material suppliers and equipment manufacturers to contractor training and insurance models, is optimized for Portland cement. Introducing a new material requires retooling this vast, interconnected system. The cost of certifying a novel concrete mix for structural use can be prohibitive, requiring years of expensive testing. This creates a powerful inertia, a preference for the known devil over the unknown angel, no matter how promising. An illustrative scenario makes this tangible. Picture a municipal engineer tasked with designing a new coastal flood barrier. Her specifications binder is filled with decades of reliable data on conventional steel reinforced concrete. She knows its exact strength at 28 days, its corrosion rates in salt water, and its maintenance schedule. The Roman-inspired alternative, with its self-healing properties and lower carbon footprint, exists only in promising research papers and a few pilot projects. For her, choosing the novel material carries professional and legal risk. The safe, defensible choice is almost always the established one. This reality forces a strategic distinction. Widespread, universal replacement of Portland cement is a distant goal. The immediate, promising frontier is in niche applications where the Roman advantages are overwhelming. Marine structures like seawalls, offshore wind turbine foundations, and underwater pilings are perfect candidates. In these harsh environments, where modern concrete fails expensively and often, a material that thrives in seawater and self-repairs could be revolutionary, justifying the upfront investment in development and certification. The research community is actively working to dismantle these barriers. Teams are experimenting with chemical accelerators that could speed up the initial set time of geopolymer mixes without compromising their long-term benefits. Other projects focus on developing synthetic or alternative pozzolans, seeking to replicate the reactive chemistry of volcanic ash using more widely available industrial byproducts or engineered materials. This work aims to decouple the recipe from specific geologic locations, making it a globally accessible technology. The conversation, therefore, must expand beyond the laboratory. Reflective questions arise about the drivers for systemic change. Could updated building codes that reward low-carbon, durable materials with tax incentives or faster permitting break the inertia? Could engineering education begin to treat Roman concrete not as a historical footnote, but as a foundational case study in sustainable material science. The shift requires policy foresight and educational evolution alongside chemical innovation. This is not a story waiting for a single breakthrough, but for a collective change in perspective, where we recalibrate our definition of value in construction from the cheapest initial cost to the lowest lifetime cost, both financially and environmentally. The good news is that this change is already beginning, not in theory, but in the rising forms of specific structures that dare to build by the old, new rules. The ancient recipe is no longer confined to history books or laboratory beakers. Its principles are now being poured into the foundations of our own century. Along the vulnerable coastlines of the Mediterranean, where erosion threatens both ancient ruins and modern communities, a fascinating hybrid of old and new is taking shape. In Italy, conservationists are using lime pozzolana mortars, carefully formulated to match the original Roman chemistry, to restore historical structures like the Roman theatre in Verona. This approach, known as compatible restoration, ensures new repairs bond seamlessly with the ancient fabric, allowing the structure to move and breathe as a unified whole, rather than creating rigid, incompatible patches that can cause further damage. This is the first crucial step, applying the wisdom not just for new construction, but for stewarding the legacy we have already inherited. The ambition, however, extends far beyond restoration. In the United States, a team from the University of Colorado, Denver, led a groundbreaking pilot project, constructing a marine-grade concrete dock piling using a Roman-inspired formula. Their mix replaced 90% of the Portland cement with a combination of fly ash and volcanic ash. After casting, the pilings were submerged in the aggressive tidal waters of San Francisco Bay. For years, researchers monitored them alongside conventional pilings. The early results were telling. The Roman-inspired samples showed superior resistance to chloride penetration and less surface degradation. This real-world test, though small in scale, provided critical performance data that moves the material from theoretical promise to documented resilience. Parallel innovations are emerging that capture the spirit of the Roman model, even if their chemistry differs. One prominent example is ductile, a type of ultra-high-performance concrete. While it uses modern materials, its design philosophy echoes that ancient pursuit of longevity. Ductile incorporates fine steel or polymer fibers throughout its matrix. If a crack forms, these fibers bridge the gap, holding the material together and allowing for something remarkable. The crack surfaces remain close enough that a process called autogenous healing can occur. Moisture and residual cementitious materials can react to seal the fissure, a modern mechanical analog to the Roman chemical process. Another frontier is bioconcrete, which embeds limestone-producing bacteria and their food source in capsules within the mix. When water infiltrates a crack, it dissolves the capsules, awakening the bacteria. As they metabolize, they produce calcite, a natural mineral that fills the crack. This is a brilliant, bio-inspired translation of the same core principle, a material designed to respond to injury with regeneration. The engineers behind these projects speak of a shared motivation, a profound frustration with the disposable nature of modern infrastructure. They describe looking at century-old bridges requiring constant, expensive repair and asking if there isn't a better way. Modern tools aid this ancient quest. Advanced computational modeling allows them to simulate the long-term chemical reactions and stress distributions within these novel mixes, something Roman builders could only intuit through generations of observation. The challenge lies in marrying this old material wisdom with new world safety standards. Every innovative mix must pass a battery of accelerated aging tests, compression tests, and durability trials to earn the certification needed for public use. It is a meticulous, slow process of validation. Consider a future where this validation is complete. Visualize a new coastal barrier. its gray surface indistinguishable from any other at first glance. But within its core, a tailored chemistry is at work. Seawater percolating through its pores isn't a threat, it's a participant, slowly encouraging the growth of strengthening minerals. Minor stress cracks from winter storms don't propagate, they quietly seal themselves by summer. The life cycle cost of this structure, when projected over 100 years, plummets compared to its conventional counterpart. This shifts a fundamental question from our engineers and civic planners. We are accustomed to building monuments of glass and steel that symbolize our technological present. But what if we began to construct the quiet, enduring infrastructure that will become our legacy to the future? What libraries, transit hubs, or energy systems would we design differently if we knew they were meant to serve not just our children, but civilizations a millennium hence? The recovery of this lost recipe invites us to build with that depth of time in mind, to choose materials that tell a story of care and endurance long after our names are forgotten. The Pantheon has been a working building every single day for nearly 1900 years. This uninterrupted service points to something far deeper than clever chemistry. It reveals a foundational Roman mindset known as Aeternitas, the pursuit of eternity. For the Romans, engineering was not merely a practical art, it was a philosophical and political statement carved in stone. Historians of technology emphasize that when an emperor commissioned a harbor, an aqueduct, or a temple, he was not just solving a logistical problem. He was projecting an image of imperial stability, civic virtue, and a civilization destined to endure. The concrete itself became a metaphor. Its slow, strengthening maturation mirrored the ideal of a state that would grow more resilient with time. Its ability to withstand the elements symbolized Rome's capacity to withstand chaos and barbarism. In this light, the Colosseum or the Aqueduct of Segovia were not just amenities, they were the physical propaganda of permanence, assuring every citizen and subject that the Roman order was as fixed and reliable as the mountains. This ideology of endurance connected all aspects of their civilization. The lasting strength of their concrete was of a piece with the enduring structure of Roman law, the far-reaching networks of their roads, and the pervasive influence of their Latin language. Infrastructure was the skeleton upon which the body of their culture was built, and they designed that skeleton to be indestructible. This creates a profound contrast with much of our contemporary built environment. We live in an age of rapid iteration and often planned obsolescence. Commercial buildings are frequently designed with lifespans of 50 or 60 years, after which they are expected to be demolished and replaced. Our material choices often prioritize speed of construction and low initial cost over multi-generational legacy. The Pantheon, by stark comparison, was designed for continuous adaptation. It began as a temple to all gods, was consecrated as a Christian church, and now stands as a museum and architectural wonder, all without its fundamental structure ever being replaced. It raises a challenging question for our own era. What do our most common building materials say about our societal values? Do they express a commitment to the future or a focus on the immediate present? This question leads directly into the modern field of preservation ethics, which faces a paradoxical dilemma created by materials like Roman concrete. When a structure is built to last for millennia, how should later generations approach its care? Is the goal to freeze it in a moment of time, or to allow it to continue its slow, chemical evolution? The concrete itself continues to cure and change, a process we cannot and perhaps should not stop. This forces conservators to make philosophical choices about what constitutes authentic preservation. Is it more authentic to replace a damaged section with a perfect historical replica, or to use a modern material that will age differently? The material's very longevity challenges our notions of stewardship. We are not merely maintaining a static relic, we are tending to a living geological process that began under the rule of Hadrian. This brings the narrative full circle, from the chemical secrets in the mix to the cultural weight they were meant to carry. The Romans built with the conviction that their world would last, and in the silent, steadfast presence of their concrete, a part of it truly has. To understand the full miracle, we must finally look closer than ever before into the crystalline heart of the material itself, where the final proof of its eternal ambition is written in mineral form. Aluminous Tobermorite is a geological rarity that should not exist at room temperature. This intricate mineral, with its perfect plate-like crystals, is the microscopic hero of the Roman concrete story, and its presence is a direct defiance of modern material expectations. Mineralogists explain that Tobermorite typically forms in high-temperature, high-pressure environments deep within the Earth's crust, or in the superheated steam chambers of industrial autoclaves used to make some modern concrete blocks. Finding it stable and abundant in a 2,000-year-old man-made material, cured under the gentle Mediterranean sun and sea, is like finding a perfectly formed diamond in a backyard garden. It simply should not be there, and yet it is the very source of the concrete's legendary strength. The secret lies in its unique crystal architecture. Under powerful microscopes, aluminous Tobermorite reveals itself as a layered structure, sheets of calcium, silica, and oxygen held together by layers of water molecules and aluminum atoms that have substituted into the crystal lattice. This layered design gives it a remarkable combination of properties. It is incredibly strong in compression, yet the bonds between the layers allow for a slight, flexible give, enabling the material to absorb stress and movement without catastrophic cracking. Think of it not as a solid, rigid slab, but as a microscopic deck of cards where each card is bonded firmly to the next, but the entire stack can flex and shift slightly under pressure. This flexibility is a key advantage over the more brittle, amorphous binders in modern concrete. The Roman process created the perfect slow-motion laboratory for growing this mineral. The aluminum, abundantly supplied by the volcanic Pozzolana ash, and the magnesium drawn from the seawater, acted as crucial chemical directors. Over decades, they guided the slow reorganization of the concrete's internal chemistry, encouraging the formation of these stable, interlocking plates instead of weaker, more disordered compounds. This is a stark contrast to the Tobermorite-like phases that can form in some modern autoclaved aerated concrete products. Those industrial versions are created rapidly under artificial heat and pressure, and they are often less stable, prone to breaking down or transforming into other minerals over time when exposed to moisture. The Roman version, grown with geological patience, achieved a stability that has lasted for millennia. This presents a tantalizing challenge for contemporary scientists. If we can learn to nucleate and grow stable Tobermorite under ambient conditions, we could potentially engineer a new generation of ultra-durable composites. Researchers are experimenting with seeding modern cement mixes with tiny, pre-formed Tobermorite crystals, hoping these seeds will act as templates, guiding the surrounding material to crystallize in the same beneficial pattern as it cures. Other teams are exploring chemical additives that mimic the role of the seawater's magnesium, trying to replicate that ancient catalytic effect. The goal is to design a material that doesn't just harden, but that begins its own long-term, strengthening crystallization process from the moment it is poured. This pursuit raises a broader, reflective question about our approach to innovation. The Romans achieved this feat not by inventing a new, synthetic material in a lab, but by orchestrating a slow reaction between abundant, local resources, volcanic ash, lime, seawater, and time itself. Their genius was in recognizing and harnessing a natural chemical potential that already existed. In our quest for faster and stronger, have we overlooked the profound power of slow, guided chemistry? What other transformative materials might we design if we shifted our focus from immediate performance to long-term evolution? learning to cultivate strength in our structures the way a forest cultivates resilience over centuries. The Tobermorite enigma is more than a mineralogical puzzle. It is a philosophy of making written in stone. The chemical genius of Roman concrete was inseparable from a logistical miracle. To build an empire in stone, Rome first had to master the art of moving mountains of raw material across vast distances with pre-industrial technology. The recipe was not just a formula, it was a supply chain, a triumph of organization that turned local geology into a global building standard. At the heart of this system was a deliberate duality, a principle of using local materials wherever possible, while ensuring the vital reactive ingredients were never compromised. For the aggregate, the coarse rubble that gave concrete its bulk, engineers relied almost entirely on local sources. If you were building a fort in Britain, you used local flint or limestone. Constructing a market in North Africa meant employing nearby sandstone. This practice minimized transport costs and embodied a pragmatic adaptability. But for the binder, the magic powder that activated it all, there was no substitute. The finest Pozzolana ash from the volcanic fields around Puteoli in the Bay of Naples was considered so superior it became a state-controlled commodity, shipped across the Mediterranean like imperial treasure. Lime production, while more widespread, also followed a logic of strategic sourcing. The purest limestone came from quarries near Tivoli, just east of Rome, where massive kilns produced lime for the capital's grandest projects. Archaeological economists studying shipwrecks and port records reveal the astonishing scale of this trade. The Roman state leveraged its existing, highly organized infrastructure for moving bulk goods, primarily grain, to transport building materials. The Annona, the system that fed Rome with Egyptian and North African wheat, often saw ships carrying pozzolana or cut stone as ballast or backhaul cargo on return voyages. This was a sophisticated early form of logistics optimization, ensuring ships rarely sailed empty. The famous cursus publicus, the state courier and transport network of roads and relay stations, while primarily for officials and messages, also facilitated the movement of specialists and lightweight, high-value components like metal tools or architectural plans, coordinating projects across provinces. To understand this system in motion, we can trace a single, documented shipment. During the construction of King Herod's ambitious harbor at Caesarea in the 1st century BCE, Roman engineers were brought in to execute the monumental underwater concrete piers. Historical sources and archaeological evidence point to a specific voyage. Ships would have been loaded at the bustling port of Puteoli with sacks of the precious pozzolana ash. Sailing south, they would cross the open sea, a journey of several weeks navigating to the coast of Judea. Upon arrival, this imported ash would be mixed with lime, likely produced from local limestone kilns, and aggregates gathered from nearby coastal quarries. The universal active ingredient, the pozzolana lime paste, was thus blended with local bones, creating a globally consistent Roman product from a fusion of imported knowledge and regional resources. This logistical framework prompts a reflective question about sustainability, not in a modern environmental sense, but in one of sheer operational endurance. The Roman model minimized energy-intensive processing by using the Earth's own volcanic chemistry. It reduced transport weight by sourcing the heaviest components, the aggregates, locally. It created a durable product that eliminated the need for frequent reconstruction and the constant movement of materials that entails. Their system valued the long-term stability of the built asset over the short-term ease of a single, uniform material. This stands in stark contrast to our modern globalized supply chains, where identical steel and Portland cement are shipped worldwide, often overlooking perfectly suitable local alternatives that could lower both carbon cost and logistical complexity. The Roman achievement forces us to consider whether true resilience in construction begins not with a universal material, but with a universal principle, adapting a core technological insight to the specific gifts of a local landscape. This adaptive genius was not unique to Rome, however, and comparing their concrete to other ancient traditions reveals why their particular chemical path led to such unparalleled endurance. The Romans did not hold a monopoly on ancient cement. Across the globe and throughout time, other brilliant civilizations developed their own remarkable binders from the earth beneath their feet. The Maya of Mesoamerica, for instance, created stunningly durable lime plasters and mortars for their towering pyramids and ornate palaces. They achieved this by burning limestone in kilns to produce lime, which they then slaked and mixed with various additives, sometimes including plant sap or ash, to improve workability and water resistance. Similarly, ancient Egyptian builders mastered the use of gypsum-based mortars, a material that sets quickly and was ideal for the precise alignment of the massive stone blocks in the pyramids and temples. These materials were sophisticated, locally sourced solutions to the architectural challenges of their specific environments. They allowed for the creation of monuments that have, in many cases, endured for thousands of years. So what then made the Roman approach so revolutionary that its structures stand apart? Archaeologists who study these comparative technologies point to a critical distinction. While many cultures perfected durable binders for above-ground, decorative, or masonry applications, the Romans systematically engineered a material for a specific, brutal purpose: massive, load-bearing construction in direct and constant contact with water. The Maya lime plaster was superb for coating walls and creating smooth surfaces, but it was not designed to form the structural core of a harbor breakwater submerged in the turbulent sea. The Egyptian gypsum mortar set rapidly and was excellent for bedding stones, but it is soluble in prolonged contact with water, making it unsuitable for aqueducts or marine piers. The Roman innovation was the deliberate incorporation of a reactive volcanic ash, Pozzolana, which transformed a simple lime mortar into a hydraulic cement, a material that not only sets underwater but gains strength from that very environment. This was a targeted chemical solution to a specific engineering problem on a colossal scale. We can see the legacy and the limits of this technology by looking at later structures. The formidable Theodosian walls of Constantinople, built centuries after the Western Empire's fall, utilized a concrete core, but one that often relied more on brick and rubble with a weaker mortar. It was an adaptation of the Roman idea, but likely without the same consistent access to premium pozzolana or the deep, hands-on knowledge of the hot mixing technique. The walls were immensely strong for defensive purposes, but they did not possess the same legendary self-healing hydraulic properties as the maritime concrete of the Caesarean harbors. Perhaps the most telling comparison lies in two iconic domes. The Roman Pantheon, completed around 126 AD, is a single, massive shell of unreinforced concrete, its aggregate carefully graded to lighten the load as it soars. Its survival is a direct testament to the material's long-term compressive strength and stability. Contrast this with the magnificent Hagia Sophia in Constantinople, built in the 6th century. Its architects, facing different material constraints and knowledge, achieved their breathtaking span with a different strategy, using lighter bricks and a special, fast-setting mortar. But the core structure is brick and masonry, not poured concrete. Both are engineering marvels, but they represent divergent technological paths, one leveraging the monolithic potential of advanced concrete, the other mastering the art of vaulting with smaller units. This divergence prompts a reflective question: how much of a civilization's architectural signature is shaped by the specific geology of its homeland? The Romans had the fortune of a peninsula dotted with reactive volcanoes, providing the key ingredient for their hydraulic revolution. The Egyptians had abundant gypsum and limestone. The Maya had rich limestone deposits, Each culture developed a brilliant technology from what was locally available, but the particular chemical properties of Italian volcanic ash unlocked a unique potential for maritime empire. This exploration of paths not taken naturally leads us to wonder, with our global knowledge and modern tools, are we now in a position to blend these ancient wisdoms, creating new materials that learn from the Maya, the Egyptians, and the Romans alike? A construction site in 2040 might look less like a dusty yard and more like a biological workshop. Here, workers are not just pouring grey slurry, they are cultivating a new kind of stone. This is the frontier where ancient Roman wisdom converges with 21st century biology and artificial intelligence, promising a revolution not just in how we build, but in what our buildings can do. The most radical innovations take inspiration directly from the Roman model of self-healing, but achieve it through programmed biology. Scientists are engineering specific strains of bacteria, like Sporosarcina pasteuriae, and embedding them with nutrient capsules into concrete mixes. When a crack forms and water seeps in, it dissolves the capsules, awakening the dormant microbes. As they metabolize, they produce calcite, a natural limestone which precipitates and fills the fissure. This is a bio-inspired translation of the Roman chemical process, using living organisms as microscopic masons. Research consortia across Europe and North America are pushing this further, exploring the potential of engineered living building materials. These are materials designed to have a metabolism. Imagine a concrete facade seeded with algae or lichen that not only self-repairs minor cracks, but also actively absorbs carbon dioxide and nitrogen oxides from the urban air, improving local air quality as it stands. This shifts a building from a passive object to an active participant in its environment, a concept futurists call metabolic architecture. Parallel to this biological revolution is a digital one, centered on the ancient chemistry of pozzolans. 3D printing with concrete or contour crafting is moving beyond simple shapes by using advanced geopolymer inks. These inks, made from industrial byproducts like fly ash activated with alkaline solutions, are the direct heirs to Roman pozzolanic chemistry. They cure rapidly with minimal heat, offer high strength, and have a fraction of the carbon footprint of conventional cement. When guided by artificial intelligence, the printer can lay down these inks in complex, optimized patterns that mimic natural structures like bone or coral, creating forms that are both stronger and use far less material. This is where computational design meets ancient material science. Experts in computational materials describe the development of digital twins for concrete structures. A digital twin is a living computer model of a physical asset, fed by a network of embedded sensors. For a bridge made with a new Roman-inspired geopolymer, its digital twin would monitor real-time stress, temperature, humidity, and even the progress of internal mineral growth. Artificial intelligence could then analyze this data, predict where maintenance might be needed decades in advance, and even suggest optimal environmental conditions to encourage the material's ongoing self-strengthening reactions. It is a feedback loop of intelligence, learning from the empirical, trial-and-error approach of the Romans, but with the predictive power of modern simulation. Startups are already bringing pieces of this future to market. Companies are commercializing self-healing bacterial concretes for critical infrastructure, while others specialize in turning industrial waste streams into high-performance geopolymer binders for 3D printing. The vision they share is of a circular construction economy where buildings are not merely assembled, but are grown and repaired from locally sourced, often waste-derived materials. Envision a city district constructed with these principles. Its structures have a subtle, textured appearance, their forms flowing and organic rather than rigidly rectilinear. Sensors are woven into their fabric like a nervous system, After a minor seismic tremor, network alerts confirm that micro cracks in several support columns have already been sealed by bacterial activity. The building's facade, treated with a photocatalytic coating that breaks down pollutants, is passively cleaning the air that flows around it. This is not science fiction. It is the logical endpoint of applying Roman durability with modern agency. It prompts a profound question about legacy. The Romans built with Aeternitas and eternity in mind, leaving monuments that spoke of their civilization's power long after its political collapse. If we now develop the tools to create infrastructure that lasts for millennia and actively improves its environment, what story will our concrete tell about us? Will it speak of an era that finally learned to build in harmony with the planet? Or will the ethical weight of creating such permanent objects force us to reconsider what and for whom we choose to build to last forever? A concrete dam built to last 10,000 years would stand as a testament to human genius, yet also as a geological fact imposed upon the landscape. This is the profound ethical weight that accompanies the recovery of a lost recipe for immortality in stone. We must now ask not only if we can build for millennia, but whether we should, and what responsibilities such power demands. Philosophers of technology point to a core tension between the ancient virtue of durability and a modern ethic of sustainability. For the Romans, Aeternitas was an imperial statement, a declaration of dominion over both space and time. Their concrete was a tool of permanence, anchoring their civilization's footprint onto the earth with an almost geological finality. Today, our understanding of sustainability is more nuanced, encompassing not just a material's longevity, but its full life cycle impact, its energy footprint, and crucially, its potential for future adaptation or gentle return to the ecosystem. The Roman drive was to build monuments that outlasted dynasties. Our challenge is to build infrastructure that serves future generations without imprisoning them in the choices of the past. This concept is known as intergenerational equity, the idea that we hold the planet in trust for those who come after us. It forces a difficult question when we design a seawall or a repository meant to endure for 10,000 years. Are we acting as wise stewards providing a gift of security, or are we arrogantly imposing a permanent constraint on the landscape and the people who will inhabit it centuries from now? An environmental ethicist might frame this as a conflict between resilience and flexibility. A harbor breakwater that self-heals and lasts for ages is resilient, a bulwark against change. But what if climatic shifts or rising sea levels render that harbor obsolete? A permanently indestructible structure becomes a massive, unmovable artifact, a form of what some scholars term technofossil. It is the opposite of the circular economy we now strive for, where materials are designed to be disassembled and reused. Roman concrete, for all its glory, was not designed for deconstruction. It was designed for eternity, which presents a unique modern paradox. How do we balance the urgent need for low-carbon, durable materials with the equally important need to avoid creating indestructible waste? Consider the illustrative scenario of that 10,000-year dam. For 1,000 years, it provides clean water and flood control, a blessing to countless generations. But after 3,000 years, tectonic shifts might change the river's course, leaving the dam as a colossal, useless barrier disrupting local ecology. After 5,000 years, the society that built it may be a forgotten memory, and the dam itself, though intact, could become a hazard, its original purpose and safe operation manual lost to time. This is not a hypothetical. We see echoes of it today with nuclear waste containment, designed to outlast human languages and civilizations. The ethical imperative, therefore, expands beyond the material's creation to include the stewardship of knowledge about it. If we build with Roman permanence, we must also build and maintain the cultural and technical institutions capable of managing, understanding, and if necessary, safely decommissioning these structures across millennia. This leads to a reflective pivot. Even the legendary Roman concrete was not invulnerable. Its true lesson may lie not in invincibility, but in its specific, elegant response to its environment. While it resisted the sea magnificently, it could still be quarried and broken down with sustained human effort. It could be damaged by catastrophic forces like direct, massive impacts or extreme, unanticipated chemical attacks. Its durability was a product of harmony with specific conditions, not an absolute defiance of all physics. The Pantheon stands not because it is indestructible, but because it found a perfect equilibrium with the Roman climate and has been meticulously cared for as a cherished space for 2,000 years. Its survival is as much a story of continuous cultural value and adaptation as it is of chemical composition. So the ultimate question becomes, what kind of future are we physically constructing? Are we building rigid, permanent assertions of our current needs, or are we cultivating adaptable, intelligent systems that can evolve, be repurposed, and ultimately, when their time has come, gracefully return to the earth? The Roman recipe gifts us the technical possibility of the former. Our wisdom must guide us toward the latter, using such durable materials not to stamp our will upon the planet permanently, but to create a resilient, generous foundation upon which unknown future generations can build their own world. Even the Pantheon has a story written in subtle wear. While Roman concrete stands as a marvel of durability, it is not, and never was, a magical substance immune to all forces of nature. To understand its true genius, we must also understand its limits, the specific conditions under which this ancient material can and does degrade. This honest examination reveals not a flaw, but the boundaries of its engineered harmony with the world. In the northern reaches of the empire, like Britannia, Roman structures faced an enemy the Mediterranean recipes were never designed to combat: the relentless freeze-thaw cycle. Water seeping into microscopic pores would freeze, expanding with tremendous force, and then thaw, repeating this destructive process season after season. This could slowly spoil and crumble surfaces, a form of stress that the concrete's self-healing chemistry, optimized for stable maritime environments, could not easily repair. Similarly, in our modern era, ancient concrete faces a new and potent adversary: acid rain. Formed when industrial pollutants mix with atmospheric moisture, this acidic water can chemically attack the lime binder, slowly dissolving it over decades. A conservation scientist studying the markets of Trajan might point to a weathered section where the surface has become soft and powdery, a condition known as sugaring. This is not a failure of the original design, but evidence of its encounter with an environmental stressor unimaginable to its builders. The material's great strength also had a hidden vulnerability tied to its own construction methods. Roman engineers often used iron or bronze clamps to hold large stone blocks or formwork together before the concrete cured. While the concrete itself resisted chloride-induced corrosion in seawater, these metal clamps, when exposed to moisture and oxygen in above-ground settings, could rust. As iron rusts, it expands, creating immense internal pressure that can crack the surrounding stone or concrete from within. This is a poignant reminder that durability is often a chain, and its weakest link determines its fate. We can see this spectrum of resilience in direct comparison. The submerged concrete of the Caesarea harbor breakwater remains remarkably intact, its chemistry activated by the sea. Yet, sections of the same city's above-ground aqueducts, exposed to centuries of weathering, agricultural runoff, and modern pollution, show significant erosion and loss of surface material. The Roman Baths complex in Bath, England, presents another case. While the overall structure survives, certain areas of mortar and concrete have degraded due to the constant combination of moisture, soluble salts from the ground, and temperature fluctuations. Studying these failures is not an exercise in pointing out flaws, but a crucial science for those tasked with preservation. By understanding exactly how and why degradation occurs, conservators can design interventions that support the original material rather than fight it. They might use shelter coats to protect surfaces from direct rainfall, or install improved drainage to divert water away from vulnerable foundations. This scientific honesty leads to a humbling and clarifying realization. No human-made material is eternal. Roman concrete does not exist in a category of magical indestructibility, but at the far end of a measurable spectrum of durability. Its true achievement was to push that boundary so far through intelligent chemistry. When we quantify its performance, we see a material designed to thrive within a specific ecological niche, the stable, mineral-rich waters of the Mediterranean and the temperate climate of central Italy. Outside that niche, its legendary resilience meets natural limits. This reframes our appreciation from one of mystery to one of precise accomplishment. It also poses a guiding question for our own building ambitions. If we seek to create materials for the ages, should we aim for a brittle, universal invincibility, or for a resilient, adaptive harmony with a chosen environment? The Roman answer, written in both its enduring harbors and its weathered walls, suggests the latter path holds the deeper wisdom. The numbers tell a story far more compelling than legend. To move from awe to understanding, we must translate the Pantheon's silent endurance into the precise language of engineering, comparing its performance against the materials that define our modern world. The most common metric is compressive strength, a material's ability to withstand a crushing load measured in megapascals. Modern high-performance concrete, engineered for rapid construction, can achieve astonishing initial strengths of 50 or even 80 megapascals within 28 days. Cores drilled from 2,000-year-old Roman maritime structures like the harbor at Caesarea consistently test around 20 megapascals. At first glance, this seems like a clear win for modernity. But this single snapshot misses the entire narrative of time. Modern concrete often reaches its peak strength quickly, and then begins a long, slow decline due to chemical attacks and internal stresses. Roman concrete, by contrast, achieved a strong baseline and then maintained or even increased that strength over centuries through its ongoing pozzolanic reactions and self-healing. Its performance curve is not a peak followed by a slope, but a plateau that gently rises. This distinction is captured in a concept engineers call functional service life. For a modern marine pier, this might be 50 years before corrosion of the steel reinforcement necessitates major repair or replacement. For a Roman breakwater, the functional service life, as evidenced by structures still performing their original duty after 2 millennia, is measured in centuries, not decades. The true superiority of the ancient material reveals itself in other, more telling metrics. One is resistance to chloride ion penetration, the primary cause of rebar corrosion in seawater. Laboratory tests on replicated Roman mixes show chloride diffusion coefficients orders of magnitude lower than standard Portland cement concrete. In simple terms, the dense, crystalline matrix of Roman concrete acts as a far more effective barrier, preventing the corrosive salts from penetrating deeply. Even more revealing is its behavior under tensile stress, the kind of pulling or bending force that causes cracks. While no concrete is great in pure tension, Roman concrete's interlocking crystal structure and ability to self-heal microcracks give it a remarkable resilience. Imagine a simple weight test on 2 concrete blocks. A modern block under repetitive, heavy loading might develop a single, catastrophic crack that splits it cleanly in 2. A Roman-style block, with its more flexible internal architecture, might develop a network of many tiny, hairline fissures that distribute the stress. More importantly, if that loading stops, the infiltrating moisture could begin to seal those micro-cracks from within, allowing the block to recover some of its integrity. This is not a brittle material, it is a tough one. Structural testing labs now use advanced acoustic emission sensors to listen to concrete under stress. In modern samples, they hear the sharp, distinct signals of large cracks propagating. In Roman-inspired mixes, the sound signature is often a quieter, more diffused chatter of micro-cracking, a sign of the material accommodating stress rather than fighting it until sudden failure. Graphs comparing long-term durability in aggressive environments like seawater tell the visual story. A line representing modern ordinary concrete drops steeply over time as strength is lost. A line for modern high-performance concrete holds steadier but still trends downward. The line for a well-formulated Roman pozzolanic concrete, however, is almost flat or even shows a slight upward trend over the 1st century, modeling its continued chemical maturation. These are not hypothetical curves, they are derived from testing ancient cores and modern replicas side by side in accelerated aging tanks. This data forces a reflective shift in how we value performance. We have optimized our world for speed and initial strength for the sprint. The Romans engineered for the marathon, for a material whose virtue was not how strong it was on the day it was poured, but how wisely it managed its strength across countless tomorrows. In a world facing the long-term costs of crumbling infrastructure and the urgent need for sustainability, which metric truly matters more? So what would the ultimate recipe look like if we could compile every clue into a single master formula? After decades of forensic analysis, experimental trials, and scholarly debate, a hypothetical blueprint for indestructible Roman maritime concrete emerges. This is not a simple list, but a synthesis of principles, the culmination of our entire investigative journey. Picture a master builder's ledger, not with exact weights, but with the essential relationships. The consensus points toward a volumetric ratio of roughly 1 part freshly slaked quicklime to 2 parts fine, reactive pozzolana ash, ideally sourced from the volcanic regions around the Bay of Naples. This lime-rich paste would then be combined with approximately 3 parts of a carefully graded, coarse aggregate, primarily angular chunks of volcanic tuff or travertine, ranging from fist-sized rocks down to coarse gravel. The mixing liquid would not be fresh water, but seawater itself, drawn directly from the construction site. The process would be a hot mix, combining the materials while the lime putty was still warm and reactive, using vigorous, prolonged kneading to coat every stone fragment thoroughly. The mixture would then be poured into wooden formwork, ideally in a tidal zone where it could cure in the alternating wet and dry environment that encourages the long-term chemical conversation. This formula is a simplified model, a best-guess reconstruction. Experts in ancient materials consistently caution that Roman practice was inherently variable, adapted to local resources and the specific demands of each project. For a freshwater aqueduct, they might have used a slightly different ash or a freshwater mix, though the pozzolanic core remained. For terrestrial structures like the markets of Trajan, the aggregate might include more broken brick and tile, and the mix could be slightly leaner on lime. The master formula represents the idealized core principles for the most demanding application, building eternities in the sea. Let us walk through the role of each component in the final, indestructible whole. The 1 part quicklime is the chemical spark, the caustic heart that, when slaked, provides the calcium hydroxide necessary to react with the ash. The 2 parts pozzolana are the transformative agent, its silica and alumina dissolving to form the durable calcium silicate hydrate binder, and over centuries the plate-like Tobermorite crystals. The 3 parts graded aggregate form the physical skeleton, the tuff and stone creating a dense, interlocking internal architecture that distributes stress and minimizes shrinkage. The seawater is the catalyst and long-term partner, its magnesium and sulfate ions guiding the formation of strengthening minerals within the pores and cracks. Imagine an animated sequence of this ideal process. First, the quicklime hisses and steams as water is added. transforming into a warm, creamy paste. This paste is immediately combined with the volcanic ash in a deep mixing trough. Workers, using heavy wooden paddles, work the thickening mixture with rhythmic, energetic strokes, the heat from the reaction warming their tools. Next, the graded aggregate, piles of angular gray and brown rock, is shoveled in. The mixing becomes a strenuous effort, folding the stony rubble into the reactive mortar until every surface is coated in a uniform, gritty paste. This mixture is then shoveled into wooden forms positioned in the shallows. Seawater laps at the forms as the concrete is placed. Over the following days, it begins to set, not with the rapid hardness of modern cement, but with a gradual firming. As the tides rise and fall, seawater percolates through the material, initiating the slow, centuries-long reactions that will weave the crystalline tapestry within. This sequence transforms the abstract ratios into a vivid, tangible act of creation. Could this synthesized formula be your guide to experiment? For the curious and the hands-on learner, it provides a starting point, a set of parameters to explore. It bridges the gap between historical discovery and personal engagement. You might not have access to Pozzolana's volcanic ash, but you could seek out a local pozzolanic material, like certain types of fired clay or industrial byproducts. The act of slaking lime, mixing a hot batch, and observing its cure over months is a direct conversation with the past, a way to physically understand the choices Roman engineers made. It turns the audience from passive viewers into potential investigators, asking what materials in their own landscape might hold a hidden, reactive potential. This journey through the lost recipe ultimately reveals that the greatest construction material ever devised was not a secret ingredient, but a profound philosophy of harmony between human intention, earthly chemistry, and the patient, shaping hand of time. The ruins spoke a silent question, and science has now provided the answer. This journey from the Pantheon's dome to the laboratory's microscope reveals a story far greater than a single recipe. It is a testament to human ingenuity, a lesson in humility, and a clear blueprint for a more resilient future. The Romans achieved their immortality in stone not by conquering nature, but by collaborating with it. They listened to the chemistry of their local landscape, using reactive volcanic ash and even corrosive seawater as partners in a slow, strengthening dialogue. Their genius was not in defying time, but in designing a material that used time as its greatest ally. This ancient empiricism, born of observation and craft, now finds its validation in the precise language of modern mineralogy and materials science. We stand at a rare crossroads where a deep past offers a direct path forward. The key takeaways are profound. We must renew our respect for the sophisticated engineering of ancient cultures, seeing their ruins not as mysterious relics, but as libraries of practical wisdom. We have a clear, proven model for more sustainable construction, one that prioritizes low-carbon materials, leverages industrial byproducts, and designs for centuries of service rather than decades of decay. And perhaps most thrilling, we are reminded that history's greatest puzzles are not merely academic, they are urgent invitations to innovate. Our modern world is shadowed by its own ephemeral creations, from bridges requiring constant repair to the staggering environmental cost of their making. The lesson of Roman concrete is a call to build differently, to think in terms of legacy. It challenges us to construct not just for our immediate needs, but for the unknown generations who will inherit our world. What if the most progressive act we can take is to learn from the oldest wisdom we possess? If this fusion of ancient insight and modern possibility resonates with you, we would love to hear your thoughts. What other lost technologies or ancient engineering marvels should we explore next? Share your ideas in the comments below and subscribe to join us as we continue unraveling the deepest mysteries of our shared human story, one discovery at a time.